So as Jiming mentioned, kind of the goal of this is to kind of put everyone on the same foundation. And one of the big feedback from last year's retreat is that a lot of people in different areas don't really understand what other people are doing. And particularly there's a lot of nomenclature that maybe, you know, the feedstock we use all the time, but people in conversion have no idea what they're talking about, and vice versa. And I think in the reviews yesterday, Madhu said it best: can we talk in regular English about our research so we can understand it? So out of the integration theme, we thought we'd do a 101 talk, and unfortunately I got chosen to lead this off. So I'm trying to do this in a very general area, and then we'll have a little bit more in-depth talk. So it's important to realize what our goal is. And our goal is we're trying to take petroleum and replace it with a renewable feedstock that at least is CO2 neutral. And I should emphasize that really our target is the production of fuels, but not really automotive fuels. And this is part of all the BRCs. And a lot of that's due to electrification of automobiles. So think about Teslas and things. But batteries aren't going to deal with long distance trucking, aerospace, shipping. You know, that's roughly about 40 to 50% of the transportation energy market. So if you think about diesel fuels, it's 40% of the market in the US, it's 60% in Europe. Ethanol is not going to replace diesel. And there's another big area, which is actually chemical production. So a large number of hydrocarbons are going to chemicals, and at least a lot of what we're trying to do is replace some of the monomers used to make plastics and different kinds of chemicals with renewable-based compounds. So I'll start off with just kind of the foundation, kind of first-generation biofuels. This is kind of the bioethanol, the 10% that's in all of our gasoline. There's really two simple processes for it. One, you can think about kind of the Brazilian process where you take sugarcane, you extract the sugarcane juice. Within that juice is sucrose, so that's a disaccharide of glucose and fructose. And then you can do direct fermentation on that with yeast to produce ethanol. So it's the same as making beer or vodka or whiskey. It's kind of that classic process that's been around for 10,000 years. There's also our process in the US, which is basically corn-based ethanol. Here, we extract the sugars directly within the corn, which is in the form of starch. This is a polysaccharide, so it's lots of glucose molecules linked together. Yeast don't naturally break down starch, so we treat it with an enzyme, so alpha amylase, that releases the different kinds of sugars in it, and then you can do a straightforward fermentation process with it. It's important to recognize, even though I had a simple diagram, that the process flow diagram for even first-generation biofuels is fairly complicated. So you have, you know, in the top part, you have kind of the digestion, so kind of production of the sugars. You have the fermentation. Once you do the fermentation, you have a solution that's roughly beer, right? So 8-9% ethanol. You still have to get that to 100%, so you have to do the separation. So that involves distillation. Typically, distillation will give you about 99% pure ethanol. You still got to get the water out, so it has to go through molecular sieves. There's also another process is that to extract value from this process, they actually recycle the yeast. So this is dry distiller grains. So it's not just the biofuel being made, it's the entire process. So they capture value in the yeast, which you can feed the different kinds of animals. Since another focus within CABBI is lipid-based chemicals, so there's also the biodiesel market. So here, you directly extract the oils from plants, be it soybean or palm oil, if you think about Indonesia. So TAG, triacylglycerides, so this is kind of vegetable oil. And here you do a direct catalytic conversion, so you do what's known as a methanol transesterification. And basically, this liberates the fatty acids from the glycerol backbone, and so you get biodiesel. So this is kind of a long chain molecule, unlike ethanol, which is a little short one. And then you make a lot of glycerol in the process. And so those are kind of our first-generation biofuels, and really what our goal is to move beyond this. And so with next-generation biofuels, what we want to do is actually directly use plant biomass. So there's a lot of sugars that are contained within the cell wall, and can we use those sugars within the cell wall and not directly use the sugars that can be used for food? This also allows us to move away from food crops to things like perennial grasses or different kinds of energy crops. And this kind of allows us to get around kind of the fuel versus fuel debate and potentially get much greater yields by directly attacking or directly exploiting that plant biomass. And the other thing is, can we move beyond ethanol? Basically, ethanol has already saturated the gasoline market. You know, as pressures increase the percentage of ethanol in gasoline. It's not a great chemical. Can we get to things that that mimic gasoline much better? And also, can we make, you know, chemicals, actually, because the economics are much better? Can we make, you know, bioplastics, and so on? So our goal is to kind of liberate the sugars contained within the plant cell wall. This sounds like an easy task, but it's actually very, very challenging. This is really what all the BRCs are working on, a lot of different approaches to this problem. So I think about this as 4 steps. The first one is biomass production. This is kind of growing the crops. I'm not going to talk about this because I actually know nothing about it. And I think Steve's going to talk a little bit more about the processes. But once you have the plant biomass, you got to extract kind of, basically the polysaccharides within the plant. And basically you have lignocellulose, which is a bunch of different polysaccharides glued together with lignin. And to release those sugars, typically we treat those polysaccharides with enzymes. So it's different kinds of enzymes, so hemicellulases, cellulases, and there's all kinds of cocktails for this. But you can't just add the enzymes directly to the grass or, you know, to the lignocellulosic material. You basically have to blow it apart. And this is really what pretreatment is about. And this is basically treating that plant biomass with bases, acids, heating it up. JB has a large effort using ionic liquids. So there's a lot of different technologies, and that's basically exposing these fibers. Once we have those fibers, then we can actually take those polysaccharides and we can treat them with enzymes and basically get the simple sugars out of it, which we can do fermentation on. Again, I've oversimplified this process. There's lots of work on different kinds of enzymes. No one enzyme does it. Different enzymes have different properties. Different kinds of biomass have different characteristics with different enzymes. So again, this is a large effort, not really within CABBI, but our other partner BRCs. And then once we have the sugars, unlike the case with first generation biofuels where we're doing glucose or sucrose fermentations, which are actually very simple sugars, we actually get a mixture of sugars. So we get a mixture of 6-carbon sugars, things like glucose, galactose, but also 5-carbon sugars, where we have xylose and arabinose. This actually creates problems for fermentation because yeast actually preferentially like C6 sugars. And so there's a lot of effort on trying to engineer yeast to actually use those 5-carbon sugars. Yeast Saccharomyces actually doesn't natively use 5-carbon sugars. So you have to do a lot of engineering to get all that sugar to get to whatever product you're making. Here I have ethanol. But there's another challenge is when you do this hydrolysis, you have this hydrolysate. So you're taking solid material and basically liquefying it. Yes, you release the sugars, but you get a lot of other compounds that are kind of toxic to the cell. And these are called inhibitors, and these limit the viability of fermentation. So one of the big challenges, at least in conversion, is engineering yeasts that are tolerant to these different kinds of inhibitors. This is one of the reasons why we're exploring Eschentenkia orientalis, because it has a natural resistance to it, but there's also been a lot of work on taking Saccharomyces and engineering it to be resistant to these inhibitors. I mentioned already that we want to move beyond ethanol. One of the great things about biology is that metabolism creates lots of different compounds, and a lot of those compounds are of economic value. And so can we engineer these organisms or even isolate natural organisms that natively produce this? This already occurs with things like lactic acid, acetic acid, citric acid. These are produced biologically. Can we do that within the context of fuel production? And one of the nice things about it is that we have the power of genetic engineering behind us. So we can bring in the power of tools like CRISPR-Cas9, but even traditional genetic engineering strategies that date back to '72. We can go in and we can modify those organisms in such a way that we can reprogram their metabolism to produce compounds that they don't want to natively produce. And here, we're again redirecting metabolism through the cell, and we really think about kind of the cell as this programmable factory that we can go in, we can modify its genome, and hypothetically get it to produce any compound of interest. Obviously, this is a challenging task, but we've made actually a lot of progress, and there's a lot of examples of cases where people have engineered organisms to produce non-native compounds at really high titers. You know, things like 1,3-propanediol would be kind of the canonical example. So I'll finish with kind of the challenges and opportunities. Obviously, the most important thing is economics. You know, can we make these things economically viable? This has been one of the big challenges with second-generation biofuels. Are these processes environmentally sustainable? You know, is there going to be a greenhouse gas reduction? You know, is there an environmental benefit to replacing petroleum? Can we produce the biomass at scale to have a real impact? There's also the challenge of efficient processes for liberating sugars. Vijay is going to talk a lot about this. And I haven't mentioned this so far, but there's also what about lignin? This is the third component of lignocellulose. You know, there's a lot of effort on can we actually get value from lignin? This has kind of been the big challenge since it's a significant component of plant biomass. You know, what about other substrates, not just sugars? And this is really kind of the plants as factories paradigm that's really driving CABBI. And we're not just looking at sugars, but can we, you know, utilize plant-based lipids? And ideally, can we produce those chemicals within the plant, right? Why do we have to do the fermentation? Can we do actually all the production within the crops themselves? And finally, technology development is slow and expensive. And a lot of our efforts on about accelerating this process so that it doesn't take decades to realize this vision. You know, can we shorten that time frame down a lot? And with that, I'll stop and I'll pass it on to the next speaker.